Okay, guys, today's warm-up question says, a force of gravitational attraction exists between you and the Earth. Which force is greater, the force the Earth exerts on you or the force you exert on the Earth?
They're both the same.
They're equal and opposite. Why? Do y'all remember?
Because, what's it called? There's always like the opposite force.
Anybody know what that law? It was one of Newton's, yeah. Yeah, it's the third one. And yes, Mason said it. Every action has an equal and opposite reaction. But it's Newton's third law. Okay, so you exert, or the Earth pulls on you, you pull on the Earth. And that is a force pair. We talked about that last semester. And we're going to kind of come back to it a little bit, but we're specifically focusing in this unit, at least today, on the universal law of gravitation. So we are going to be talking about that force due to gravity today that exists between objects and how we can figure out how much force exists between those objects. And then the other part of this unit is circular motion, which we will be looking at next week. They do go together. We will talk about how those two go together next week. But let's go ahead and get to our notes today on universal law of gravitation. So again, hopefully you have some paper out so you can copy this down. But there is a force of gravitational attraction between any two objects with mass. And the universal law of gravitation puts numbers to this. It allows us to figure out the relationship between the amount of mass that the objects have and the force of gravity that exists between them. And it's not just based on mass, but it is at least partially based on mass. It says here that the gravitational force that exists between any two objects is directly proportional to the product of their masses. And since we have two objects, we're going to be calling them 1 and 2, or M1 for mass 1 and M2 for mass 2, and inversely proportional to the square of the distance between them. Okay, and so this is basically writing out an equation in a sentence, which you can do, but you could just copy down the formula and it will tell you the exact same thing. But you do need to be familiar with those relationships between mass and the force that exists, and between the distance of separation and the force that exists gravitationally between two objects. This is your equation underneath my little picture there. And again, just like we said in the warm-up, those forces are equal and opposite. So F1 and F2 are equal to each other, but both of them are equal to that equation. It's a capital G. That's not the same as the lowercase g we've been using. Capital G is our gravitational constant, and it has a value, you can see it at the bottom of my screen, of 6.67 times 10 to the negative 11th. And it has some really complicated looking units. I put the units over here. Newton meters squared per kilogram squared. When we look at those units, that tells us a couple of things about the numbers, and rather the units for those numbers that we need to be using when we use this equation. Whenever you plug into the universal law of gravitation, which again, capital G, so it's our constant, times M1 times M2 divided by the distance of separation squared. That's R squared. Okay, that means if we look at the units for G, it means that our masses have to be in kilograms so that they can cancel that kilogram squared down there. And that our distance of separation, R, needs to be in meters so that it can cancel that meters squared, leaving us with just newtons remaining. But that does mean that if you're reading a question, since we're going to be talking about not just you and the Earth, but we're going to be talking about like the Earth and the Sun, or the Earth and the Moon, or other planetary bodies, usually we don't measure our distances in meters because those things are really far apart. So you'll see kilometers a lot, and you will have to do a conversion if you see kilometers before you can plug into the equation. And again, that unit gives you a clue that you're going to need to do that. Newton meters squared per kilogram squared. But again, still a force pair. The forces are equal and opposite. You can see it diagrammed up here, M1, M2. Even though M1 is bigger than M2, the forces that exist between them are equal and opposite, just like between you and the Earth. Obviously, the Earth is a lot bigger than you are. Yes, sir?
Does that work with two objects that are not like the Earth?
It does not have to be the Earth and another object. Any two objects with mass will have a force of gravitational attraction between them. All right, force of gravity is dependent upon all of the following, and you can see this just by looking at the equation, but it will be dependent upon the masses of the objects. So again, any two objects with mass will experience a gravitational attraction, and that mass is going to be directly proportional to the force. So if I say, hey, if you double the mass of, whatever, object 1, what happens to your force of gravity? You would need to tell me that it would double as well. And you can see it mathematically if you just look at that equation. The other factor that affects the amount of your gravitational force is the distance between the objects. Force and distance have an inverse square relationship, and again, you can see that when you look at the equation because you're dividing by that distance squared. If you were to double the distance, for example, you'd be not just dividing by 2, but by 2 squared. So it'd be 1/4 as much if you were to double the distance between two objects. The gravitational force drops off pretty significantly because of that inverse square relationship. Okay, so again, you need to be able to answer questions about those types of proportional reasoning, like this one. Okay, it says, which force is greater, the force on you or the force on the earth? We already answered this in the warm-up question. They are equal. It's a force pair. Okay, but look at the equation you wrote down in your notes, or at least hopefully you wrote it down in your notes. When you double the mass of one object, how is that force of gravity affected? What did we say? I just said this. Yeah, it doubles. Okay, it doubles because we have a directly proportional relationship. So be able to answer this type of question. Doubling the mass also doubles Fg. It's directly proportional. Okay, as the objects are moved closer to each other, how does the force of gravitational attraction compare? Is it going to be more gravitational attraction, less, or the same amount if you move objects closer together? More. Okay, if they're closer together, you're dividing by a smaller distance, and dividing by a smaller number, of course, gives you a larger answer. And so you would expect that you'd have a greater amount of gravitational attraction when those objects are closer together. On the other hand, if you were to double the distance between the objects, meaning you have moved it farther away, how does the force of gravitational attraction compare?
Less.
What did we say? It's less, but by what factor?
By
1/4. Again, that's the example I said a second ago. Because you're dividing by this r, again, you're not just dividing by 2, you're dividing by 2 squared. And so it would be 1/4 as much in terms of your gravitational attraction. So doubling the distance will quarter or give you 1/4 the amount of Fg. It's an inverse square relationship. Okay, so again, I've already given you those examples, but copy them down if you need to, because you will see questions like that again. All right, another note that you might want to make is that distance of separation has a greater impact on the force of gravity than mass does. And you can see why if you look at the formula. That's because that distance of separation is squared. So if you double the distance, for example, versus doubling the mass, doubling the distance is going to change things by a factor of 4, or rather 1/4. Okay, whereas doubling the mass is only going to increase things by a factor of 2. So if you're looking at which is, I guess, more important, if you will, in determining, or which has a greater impact in determining your force of gravity, it's going to be your distance that has a greater effect on it than your mass does. And again, it's in the equation, it's because it's squared. All right, so let's try just a few more examples. It says 2 objects with masses big M and little m are separated by distance r. How does each of the following changes affect Fg? Okay, so here's my original initial picture, and then here's the change. Number 1 says we have 1/3 the distance between them. So what would that do to Fg if you had 1/3 the distance? First, let's start here. If you bring them closer together, are you going to have more or less Fg? More. Okay, cool. How much more?
3 times.
Not 3 times.
1/3 more.
Not a third more. 9 times. Guys, if you divide by a third, right? You divide by a fraction, you're really multiplying by the reciprocal. So you're multiplying by 3, but again, it's not just 1/3, it's 1/3 squared. So you're not just dividing by 1/3, you're dividing by 1/9. So when you do that, you're multiplying by 9. It would give you 9 times the FG. Again, you need to be able to answer questions like this. So if you weren't sure about that one, write it down. Number 2, the distance isn't changed in number 2 from the original, but one of the masses is. I doubled it. We've already talked about that example. Doubling the mass is going to double FG. What about number 3, doubling the distance between them? Quarters it. Yeah, we already talked about that one too. Okay, I could change some of those numbers. But that is, again, the type of question you might see, unless, of course, I give you a calculation. Okay, but in each numbered scenario, which object, little m or big M, experiences more force?
Equal.
Yeah, don't fall for it. They're equal. It's still a force pair, just like it was in the warm-up, just like it was last semester. Okay, these are equal and opposite forces. Even if you make one of them bigger, doesn't matter. The force between them, they're still equal to each other. Now, the force between them will be larger, 2 times, if you double the mass of one of them. But both of them are experiencing 2 times more force now. They're still equal to each other. All right, so we can talk about, 2 planetary bodies, the Earth and the Moon, whatever. But we can also talk about things on the surface of a planet, like us and the Earth in our warm-up question. When objects are on the surface of a planet, how do you determine your distance from the planet's center of mass? How far are you from the center of the Earth?
Decent distance.
Sorry?
Decent.
Yeah, but how would we, what would we need to know?
The diameter.
The diameter of the Earth, specifically though, not actually the diameter, the radius, right? Okay, and so we would need to know the radius of the Earth, and if we're standing on the surface, our distance from the Earth's center is roughly equal to the average radius of the Earth. That's why in our equation it uses an R for distance, because it's the radius of that planet, or the radius of an orbital path, which we'll talk more about later. But you would use the radius of the planet, technically plus the radius of you to your center of mass, so like, an extra meter. But that extra meter is not really going to matter when you're comparing your size to the Earth, so just for simplicity, you can just use the Earth's radius for this, because all those objects are so much smaller. Okay, so whenever you're actually trying to solve this for something on the surface of the planet, this is obviously not drawn to scale, otherwise that we'd have a problem, because that's a really giant man. But it says an astronaut stands on the ground outside of NASA. If he has a mass of 82 kilograms, what is the force of gravitational attraction between him and the Earth? The Earth has a mass of 5.97 times 10 to the 24th kilograms and a radius of 6,378 kilometers. So we have some values, we have an equation, we can go ahead and start plugging these in. It doesn't really matter which object you call 1 and which object you call 2. So if you want to call the astronaut 1 and the Earth 2, that's fine. If you want to call the Earth 1 and the astronaut 2, that's also fine. I went ahead and called the astronaut object 1. Here's his mass, 82 kilograms. And the Earth object 2, here's the Earth's mass, 5.97 times 10 to the 24th. However, I did not divide by 6,378 squared, because that is in kilometers. So before you square it, it has to be converted. So again, there are 1,000 meters in a kilometer, so all I did was multiply that number by 1,000. 6,378 kilometers is 6,378,000 meters. Okay, that's why your 1 meter wouldn't really make a difference to your center of mass. Okay, but if you take a look at this, and I would strongly encourage you to type this in the calculator. Sometimes students have problems with this unit or with the math simply because they're not typing their scientific notation correctly. So if I were you, I would just make sure that you are comfortable typing scientific notation in whatever calculator it is that you are using. But if you type this, you end up with this, 802.7 newtons. Anybody know that there's a much shorter way to solve this particular problem?
Multiplied by 9.8.
Yeah, mass times gravity. Guys, we just solved for FG in a way more complicated way.
Actually, I was thinking that.
You were correct. Okay, you could have just done his mass, 82, times gravitational acceleration, 9.8. It's probably a little off because of rounding, because, the Earth's radius and mass aren't exact to those values. But you would have gotten the exact same answer. But sometimes you can't do that. If you're not on the surface of the Earth, you wouldn't be able to do that. Or if you're on a different planet where you don't know the gravitational acceleration, you would need to use an equation like this. Yes, ma'am?
So if it's Earth, can we just do the 9.8?
If you're solving for your FG on Earth, yes, you're welcome to multiply your mass by 9.8, and that is a much shorter way of solving this exact same problem. All right. Okay, but if you have an object at a distance, that's no longer an option, because taking your mass and multiplying it by 9.8 only works if you're on the Earth's surface. Because if you're not on the Earth's surface, gravity's not 9.8. Okay, so if you have objects at a distance, now I have my same astronaut and he's working in the International Space Station in orbit around the Earth. If the orbit height is 409 kilometers, find FG between the astronaut and the Earth. The Earth still has the same mass, 5.97 times 10 to the 24th kilograms, and the same radius, 6,378 kilometers. Okay, but now we're not on the surface. So now, if I want to figure out how far I am away from the center of the Earth, I have to add the radius of the Earth plus the height he is above it. Okay, and 409 kilometers is a fairly significant amount. So this is now the distance he is from the center of the Earth, 6,787 kilometers. That's the value we're going to use for the distance of separation between our objects. And obviously, if you're doing objects even farther away, your distance is going to be even greater if you did like Earth to the moon, for example. Okay, so again, we're going to plug into this equation. It's going to look pretty much like the last one, except this number down here in my denominator is different, and I will get a different answer, obviously. But if I type this into the calculator, I'm going to get 708.9 newtons. So he weighs a little bit less when he's in space, which again makes sense because we think of things in space as being weightless. Now he's not weightless, obviously, okay, but it is definitely less whenever you are in orbit around the Earth. And obviously as you get farther and farther away, that number is going to get smaller and smaller and smaller. Questions about this one? No? I'll give you all a moment to finish copying. It looks like some of you are still writing. But yes, if you don't have an object on the surface of the Earth, you definitely have to use this equation. But if it's on Earth's surface and you know its mass, you can go ahead and multiply it by 9.8, and it'll give you actually probably a more precise answer than this equation will, because this equation we're rounding a lot on the mass of the Earth. Okay, because we're only including those two decimals, but it's times 10 to the 24th, so there are so many digits that we don't see. All right, guys, so that is it for today's notes. For the rest of the class period today, you are working on the assignment 801.1 gravitation problem set. It is due by 11:59 p.m. tonight. Real quick, a lot of your answers that you're going to get, y'all listen up for just a second. Because we're going to be dealing with these things where we have these giant numbers or these small numbers, a lot of your answers are going to be in scientific notation. So when you go to enter them in the computer, and I have this up here on my screen for a reason. First of all, I have to grade you according to significant figures. Because if I ask you to give me like two decimal places and your answer is 5.97 times 10 to the 24th, you can't even see the digits, much less the two decimal places that would be at the end. So instead, I'm going to ask you for basically two decimals in your coefficient. Okay, so like this, for example, if this is what your calculator gives you, 3.71923 times 10 to the negative 7th, like let's say that's your answer, you can type it like this, 3.72 capital E. It does have to be capital, but this is the calculator's notation for scientific notation, negative 7. And this means 3.72 times 10 to the negative 7th power. Okay, so that's how you're going to enter it in. It does have to be rounded right. If you were to type 3.71 e negative 7, it will count it wrong. So you have to round correctly. Be careful that you don't lose points for stuff like that. If you have questions as you're working, let me know, but I'm going to stop talking, let you guys get to work, and that way you shouldn't have to take any of this home for homework because you have half an hour and the assignment is not very long. Okay, but if you have questions, please ask.